Let's have a look at the famous equation E equals mc squared. What does it mean? What are the implications of this equation? So E is energy in joules, m is mass in kilograms, and c is the speed of light in meters per second. And as we all know, it's a big number. It's 3 times 10 to the 8 squared. So that means that in a tiny mass, like in the mass of a single atom, there is an enormous amount of energy stored. This is what gave birth to the atomic age. And the two fundamental ways of exploiting this energy, the nuclear energy, are known as fusion, that means the energy of the stars, and fission, the energy that we use in nuclear generators, power stations, and bombs. So I'm going to share with you 2 movies to watch. One has to do with the consequences of fission, and the other one with the consequences of fusion. There's 2 different approaches to nuclear energy. These are a must. So at the end of this video, please click the links. Now let's look at 2 concepts, mass defect and binding energy. Let's start with mass defect first. Let us define a mass unit that is more or less good for this scale that we're using, the atom. So let's define it as 1/12. A unified atomic mass, by definition, is 1/12 of the mass of carbon-12. So that's an arbitrary definition. Why did we choose carbon? Well, it's a very popular and well-known atom, right? So that means that one unified atomic mass is the equivalent to 1.661 times 10 to the minus 27 kilograms. Tiny, tiny, tiny mass. This is all copied from the data booklet. So we can also see there in the data booklet the mass of one electron is 0.000549 unified atomic masses. The mass of the proton is very close to 1, but not exactly 1. So one proton is 1.0727. 6 unified atomic mass. The mass of a neutron is 1.008665 unified atomic masses. This is quite interesting because if we multiply these are the constituents of an atom of carbon. If we multiply by 6, there are 6 electrons, 6 protons, and 6 neutrons in an atom of carbon. And then if we add the protons and the neutrons that make the nucleon or the nucleus of the atom of carbon, we find that the nucleus is greater than 12. It's 12.09564. So the components of the nucleus added together give 12.09564 unified atomic mass. And then if we take away because we said the atom of carbon has a mass of 12, so if we take away the 6 electrons, we get that the nucleus of carbon-12 has 11.99670 unified atomic masses. Surprising result. The separate constituents have a greater mass than the package that makes the nucleus. So this is something that we need to write in order to understand the concept of mass defects. When the 12 nucleons means protons and neutrons, right, are bounded like in a package together, the mass of the 12 separate components is greater than the package, or the mass of the package is less than the separate components. So 1 plus 1 is not 2, right? We have a proton and a neutron, we add them together, and the result is less mass than if they were separated. So this is what we call mass defect. And that mass defect is going to be the one that is transformed into energy. So let's put here the definition of mass defect. It's the difference between the separate components and the components in a nucleus making that package. Okay, now let's look at mass defect and binding energy per nucleus. This video that I am putting here is a must, very interesting 9 minutes video that explains by analogy the energy needed to separate a rocket from the Earth could be seen as the energy needed to separate a nucleus or a nucleon from its nucleus. That's an analogy, and that is what we call the total binding energy. And if we want to say it per nucleon, all we have to do is divide the total energy needed to break that nucleus by the number of nucleons. Remember that the number of nucleons is the atomic number. And this energy is measured in mega electron volts. All right, so let us continue with the example that we started before. We look at carbon atom and we look at the total energy needed to break the nucleus of carbon. So the mass defect we measured was the difference between the package and the separate constitutions, 0.98940 unified atomic mass. And that you have to multiply by c squared. But we don't want the unified atomic mass in kilograms. It's a very small number. So we're going to use mega electron volts over c squared as a unit of mass that is more appropriate and easy. The data booklet tells us that 1 unified atomic mass is equal to 931.5 mega electron volts over c squared. Therefore, the total energy is the mass defect multiplied by the conversion to that unit with the benefit of simplification of c squared. So the answer comes straight in mega electron volts, 9216 mega electron volt. But that is the total energy. If we want to find the energy per nucleon, we need to divide the total energy by the number of nucleons. Remember, nucleons means protons and neutrons. So the atomic mass, A. And that gives us a result of 92.16 divided by 12, 7.680 mega electron volts per nucleon. And this is a useful number that is describing the carbon atom. So if we do this for all the atoms in the periodic table, we could go and make a graph. And that is what's coming. So this is a very important graph. You need to memorize what's in the coordinates and the general shape of the graph. You also need to know that the x is the atomic number and the y is the mega electron volts per nucleon. The binding energy per nucleon, there is a peak. That means the maximum binding energy for iron, around 60 unified atomic masses. That makes iron the most stable atom in the universe. Yeah? An atom that cannot decay. So everything tends to iron. Any unstable atom that is heavy will try to release radioactivity to become more stable and become more like iron. And the small atoms will tend to fuse to get more stability. So these are the two possibilities, fusion and fission. Let's look at fusion first. Let's look at the fusion of deuterium. Deuterium is an isotope of hydrogen, 1 proton, 1 neutron, and helium, an isotope of helium, helium-3. They combine together, they collide together, they fuse together to create an atom of helium-4 and a proton. So this is the fusion reaction. Conservation of mass, 4 plus 1, 3 plus 2. Now let's look at the energy involved in this, and we do the same thing that we did before. So we want to quantify how much energy is released by a single fusion of a single atom, or let's say a single atom of hydrogen and helium. This is what happens inside the stars. If you multiply this amount of energy by the number of atoms present in a star. That explains the enormous amount of energy that is released. So we're looking at the masses of the individual components before fusion. That's deuterium plus in unified atomic mass, and then we'll convert it, plus helium-3. I'm copying this from the table, and that is the initial mass, and the final mass we need to subtract from this the mass of helium and the mass of a proton. Let's put it down there. I'm looking at the values from the table of data. No one is expected to memorize these things. All right. So when we add all this and then we subtract what we had before and what we have after, we have a mass defect of 0.0197 unified, 0.04 unified atomic masses. Yeah. Now, if I want to calculate the energy, all I have to do is multiply that by the speed of light, but we need to convert unified atomic mass into mega electron volts over c squared. So that's per unit atomic mass, right? So the unit atomic mass cancels, and the mega electron volts over c squared, when you multiply by c squared, they simplify, and we get the answer in mega electron volts. 18.4 mega electron volts for every single fusion. Now let's look at another way of doing this, looking at the data. Here they're giving us the binding energy per nucleon for each one of the nucleus involved in this fusion reaction, right? First of all, remember that a proton has no binding energy. So the total binding energy is going to be the binding energy of helium-4 minus the added binding energy of the nucleus of hydrogen-2, deuterium it's called, and the helium-3. So we're looking at another way of solving the same question: how much energy is released? But remember, this is total binding energy. Ojo, like we say in Spanish. Don't make mistakes. Be careful. Look at this carefully, right? We have the binding energy per nucleon, right? And we need to look at the total binding energy. So we are expecting a total binding energy in helium of 4 times the binding energy, because helium has 4 nucleons, right? The total binding energy is that. And then the total binding energy of hydrogen is 2 times the binding energy per nucleon of hydrogen. I'm going to put here brackets, then add everything. And the binding energy of helium-3, 3 times the binding energy per nucleon. So we need to multiply by the number of nucleons involved. And when we do this, I'm going to do it mentally. Let's see, 18.4 mega electron volts. That is the way nature works. It is always true. Signed by Albert Einstein. All right, so we do the same thing now for fission. We're looking at how a neutron bombards uranium-35 atom to make an unstable isotope of uranium that ends up breaking in halves in 2 parts, giving krypton and barium, and 3 neutrons that will go ahead and shoot other uranium masses, creating a chain reaction. So we're going to do the same. We're going to look at the mass defect to calculate the energy. So we add the different masses. First the mass of the neutron plus the mass of uranium-235, and then the final end products, the barium and the krypton and the 3 neutrons. So that is the mass before and after the collision, the fission, I would say, more than collision, the explosion if you want. I am just copying the values from the table in terms of mass, and barium, let me think, yes, 1429 plus krypton 889. So you see, you have to use all the decimal places here. You can't just round up to 1 or 2 significant figures because there is nothing happening. So this is what we have. This is, sorry, I said energy. This is mass. This is mass defect. If we want to find the energy, we need to multiply again the mass defect by c squared, and we're going to transform units, unified atomic mass, by 9315.5 mega electron volts over c squared, and that gives us 173 mega electron volts. So a lot of energy is released. An alternative method could be looking at the same thing we did before. I don't want to do it. I'll do it mentally. 173.3 mega electron volts is what comes from the binding energy per nucleon. Remember that in this case you need to multiply the binding energy per nucleon by the number of nucleons. So let's go to the checklist. Done, 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 done. Okay, I'm going to give you time to slowly go through this checklist and tick it yourself. This is what the IB wants you to know in topic 7.2. Blessings.